If you are watching this from somewhere in the United States, maybe from a quiet suburb in Ohio, a high-rise apartment in New York City, a ranch in Texas, or a coastal home in California, look up at the sky tonight and imagine something unsettling. Somewhere out there, circling another star in the Milky Way, there could be a planet almost identical to Earth. On that planet, there could be cities glowing in their own version of electric light. There could be scientists scanning the sky, asking the same question we ask, are we alone? But here is the part that changes everything. What if the reason we have never seen them, never heard from them, never detected a single confirmed signal, is not because they do not exist, but because the universe itself has made contact physically impossible? Not difficult, not unlikely, impossible. What if the laws of physics are not just inconvenient obstacles to overcome with better engines and smarter technology, but absolute walls built into the fabric of reality? Tonight, we are going to explore a possibility that is far more unsettling than alien invasions or hidden spacecraft. We are going to explore the idea that every intelligent civilization in the galaxy may be permanently trapped inside its own star system, separated by distances and physical limits that nothing, not even a billion years of technological progress, can ever overcome. And if that is true, then the silence we hear when we search the cosmos is not empty. It is sealed. Before we drift further into the vastness, take a moment to support Calm Space to Sleep. If you enjoy slow, thoughtful explorations of the universe, gently press subscribe, leave a like, and tell us in the comments which part of the country you're watching from. Are you under the desert skies of Arizona, the forests of Oregon, the plains of Kansas, or somewhere along the Atlantic coast? It's always grounding to remember that even as we talk about cosmic isolation, we are still connected here on Earth. Now let us begin with something deceptively simple: distance. The nearest star beyond our Sun is Proxima Centauri, part of the Alpha Centauri system, and it is approximately 4.24 light-years away. That number sounds manageable until we slow down and define what a light-year truly represents. A light-year is not a unit of time. It is a unit of distance, the distance light travels in 1 year. Light moves at about 186,282 miles per second. In a single second, it could circle the Earth more than 7 times. In 1 minute, it travels over 11 million miles. In 1 year, light covers nearly 6 trillion miles. So when we say Proxima Centauri is 4.24 light-years away, we are saying that even light, the fastest thing allowed by the laws of physics, takes more than 4 years to get there. Now consider the fastest spacecraft humanity has ever built. The Parker Solar Probe, launched by NASA to study the Sun, can reach speeds of about 430,000 miles per hour at its peak velocity. That sounds extraordinary, and by human standards it is. But compared to light speed, it is glacial. At that speed, it would take thousands of years to reach the nearest star. Thousands. And that is just the nearest one. The Milky Way galaxy itself is about 100,000 light-years across. If an alien civilization existed on the opposite side of our galaxy, even a signal traveling at light speed would need 100,000 years to cross the distance. Civilizations rise and fall on timescales far shorter than that. This is where the first true barrier emerges. It is not simply that space is big. It is that space is staggeringly, incomprehensibly vast beyond the scale our brains evolved to understand. Our minds are comfortable with miles, perhaps with continents, maybe even with the distance to the moon at 238,000 miles. But once distances reach into trillions of miles, intuition collapses. And interstellar travel is not like crossing an ocean. There is no air to breathe, no nearby resources, no gravitational anchor points to use for rest stops. Between stars lies interstellar space, a near-perfect vacuum with scattered atoms, cosmic rays, and microscopic dust grains moving at tremendous speeds. Even at a fraction of light speed, a grain of dust becomes a bullet with explosive force. A spacecraft traveling at 10% the speed of light would experience impacts that release energy comparable to high-powered explosives. Shielding against this is not trivial. It requires enormous mass, and enormous mass requires even more energy to accelerate. Energy is the next barrier, and it may be even more absolute than distance. To accelerate an object to high speeds requires kinetic energy. The formula for kinetic energy in classical physics is 1/2 mass times velocity squared. That squared term is critical. Double the velocity, and the energy requirement increases by 4 times. Increase the velocity tenfold, and the energy requirement rises by 100 times. When approaching significant fractions of the speed of light, relativistic effects make the energy requirements grow even more extreme. To accelerate even a modest spacecraft weighing a few hundred tons to 10% of light speed would require energy comparable to the total annual energy consumption of entire nations. To reach 50% of light speed would require energy on scales rivaling global output over many years. And that does not include the energy needed to slow down upon arrival. Interstellar travel is not simply about going fast. It is about accelerating, surviving the journey, and then decelerating safely at the destination. Each of those phases multiplies the required energy. Some propose antimatter as a solution. Matter-antimatter annihilation is the most energy-dense reaction we know, converting nearly all mass into energy according to Einstein's equation E=mc². But producing antimatter is extraordinarily inefficient. Current particle accelerators can create tiny amounts, but the energy required to produce antimatter vastly exceeds the energy you would get back from using it as fuel. Scaling that up to the levels required for interstellar travel is beyond any foreseeable industrial capacity. Even if a civilization were thousands of years more advanced than ours, it would still be bound by the same thermodynamic realities. The laws of physics do not soften with intelligence. They do not grant exceptions for ambition. Then there is the speed of light itself. In everyday life, we think of speed limits as arbitrary rules, posted signs on highways that could, in theory, be raised. But the speed of light is not like that. It is not a suggestion. It is woven into the structure of space-time. According to Einstein's theory of relativity, as an object with mass accelerates closer to the speed of light, its relativistic mass effectively increases from the perspective of an external observer, requiring more and more energy for further acceleration. At the speed of light, the required energy becomes infinite. Infinite energy is not merely impractical, it is impossible. This means that no object with mass can ever reach, let alone exceed light speed. Science fiction often imagines warp drives or wormholes, shortcuts through space-time. These ideas arise from legitimate solutions to Einstein's equations, but they require forms of matter with negative energy density, so-called exotic matter, that we have never observed in usable quantities. Even if such matter exists, stabilizing a wormhole or warp bubble may demand cosmic-scale energies equivalent to the mass of entire planets or stars. Now consider time. Even if an alien civilization could send a spacecraft at a significant fraction of light speed, time dilation would alter the experience of the travelers. From their perspective, the journey might take decades. From the perspective of those left behind, and from us, it might take centuries or millennia. Civilizations are not static. On Earth, recorded human history spans only a few thousand years. Technological civilization as we recognize it has existed for barely more than a century. Imagine launching a mission that will arrive at its destination in 10,000 years Earth time. What confidence could any society have that its language, culture, or even biological form would remain recognizable by then? The travelers might arrive at a planet long after the originating civilization has changed beyond recognition or vanished entirely. Communication becomes equally fragile. A message sent across 1,000 light-years is a message to the distant past or future. If both civilizations do not overlap in technological capability and temporal existence within a narrow window, they will miss each other completely. Two civilizations separated by 5,000 light-years could both exist for 1,000 years, yet never know the other was there if their periods of technological activity do not align precisely. Radiation presents another silent barrier. Interstellar space is permeated by cosmic rays, high-energy particles accelerated by supernova explosions and other violent astrophysical events. On Earth, we are shielded by our atmosphere and magnetic field. In deep space, that protection vanishes. Over long durations, radiation damages biological tissue, increases cancer risk, and degrades electronics. Shielding against cosmic radiation requires thick layers of mass, perhaps water or specialized materials, which again increase spacecraft weight and therefore energy requirements. For journeys lasting centuries, the cumulative radiation exposure becomes a profound biological threat. Some suggest generation ships as a solution, massive self-contained habitats that travel slowly, carrying multiple generations who live and die during the journey. But this concept introduces psychological, sociological, and ecological challenges that may be insurmountable. Maintaining a closed ecological life support system for centuries without failure demands near-perfect recycling of air, water, and nutrients. Even small imbalances could cascade into collapse. Social cohesion across generations inside a confined artificial world may fracture. Future generations might question the mission, reject its goals, or face unforeseen cultural transformations. The probability of failure increases with time, and interstellar journeys require immense stretches of it. When we add these barriers together, distance, energy, radiation, relativistic limits, ecological fragility, temporal misalignment, the picture begins to sharpen. The universe is not merely large. It is structured in such a way that crossing between stars may be fundamentally prohibitive. This does not mean alien life does not exist. In fact, statistical reasoning suggests it likely does. Our galaxy contains hundreds of billions of stars. Many of those stars host planets. A significant fraction of those planets reside in habitable zones where liquid water could exist. The chemistry of life appears to arise readily under suitable conditions. Yet even if microbial life is common and intelligent life emerges occasionally, each instance may remain forever confined to its own stellar neighborhood. This possibility reframes the so-called Fermi Paradox, the question famously summarized as, "Where is everybody?" The paradox assumes that if intelligent life is common, it should spread across the galaxy over millions of years. But that assumption depends on interstellar travel being feasible. If the barriers we have discussed are absolute rather than temporary engineering problems, then the silence is not paradoxical at all. It is expected. The galaxy may be filled with isolated islands of awareness, each separated by oceans that cannot be crossed. As we continue this journey, allow your thoughts to expand with the scale of it. Imagine countless civilizations gazing outward, building radio telescopes, launching probes, perhaps even dreaming of starships. And imagine that each one eventually confronts the same realization. The speed of light is not negotiable. Energy is not free. Time does not wait. The cosmos may be generous in creating life, yet ruthless in keeping it apart. And if that is true, then Earth is not just our home by circumstance. It may be our home by necessity. The possibility that interstellar isolation is not merely a technological challenge, but a structural feature of reality itself, a condition woven into the architecture of the cosmos from the moment space-time began expanding nearly 13.8 billion years ago. When we look at the observable universe, we are not just looking across distance, we are looking back in time. Every star we see is an image delayed by light's finite speed. Some of those stars may no longer exist. Some civilizations, if they ever arose, may already be gone. This introduces a quiet but devastating constraint on contact. Simultaneity across cosmic scales is an illusion. Even if intelligent life appears frequently, the overlapping window during which two civilizations both possess advanced technology and the desire to communicate may be vanishingly small. On Earth, our ability to transmit detectable radio signals has existed for just over a century. Already we are transitioning to communication systems that leak less energy into space. If our detectable phase lasts only a few hundred years before evolving into quieter technologies, then the bubble of Earth's radio presence is only about 100 light-years wide. In a galaxy 100,000 light-years across, that is not even a whisper, it is a microscopic ripple. Any civilization outside that narrow sphere would not yet know we exist, and even within it, the timing would have to align perfectly for them to notice and respond before we potentially go silent. There is also the problem of cosmic hazards. The Milky Way is not a calm, empty backdrop. It is an environment shaped by supernova explosions, gamma-ray bursts, stellar flares, and gravitational disturbances. A gamma-ray burst occurring within a few thousand light-years could sterilize planetary surfaces, stripping atmospheres and collapsing ecosystems. Such events may periodically reset biological progress across entire regions of the galaxy. If intelligent life is repeatedly interrupted by cosmic catastrophes, then long-term technological expansion becomes even less likely. Civilizations might arise, advance, and then vanish before they ever attempt interstellar travel. From this perspective, the galaxy may be less like a continuously populated landscape and more like a field of candles flickering on and off in darkness. Even if a civilization survives long enough to attempt expansion, it must confront not only physics but economics and motivation. Interstellar travel is not simply a scientific project. It is a civilizational commitment requiring immense allocation of resources over centuries or millennia. On Earth, large-scale projects are constrained by political cycles, economic pressures, and shifting public priorities. Now extend that instability across hundreds of years. Would any society maintain unified commitment to a mission whose outcome none of its initiators will live to see? Perhaps some could. But the probability that most would is uncertain. The larger and more complex a civilization becomes, the more fragile its coordination may be. Technological sophistication does not automatically guarantee long-term stability. There is also the unsettling possibility that advanced civilizations turn inward rather than outward. As virtual realities, artificial intelligence, and internal digital worlds become more immersive and rewarding, exploration of physical space may lose its urgency. If a society can generate entire universes of experience computationally, the harsh vacuum between stars may appear comparatively uninteresting. In that case, the absence of alien visitors is not due to impossibility alone, but to choice. The stars remain distant because no one finds sufficient incentive to bridge them. The universe could be full of intelligence that has simply decided not to travel. Another factor is the expansion of the universe itself. On the largest scales, galaxies are receding from one another due to cosmic expansion. Beyond a certain distance, objects are moving away from us faster than light relative to our frame of reference, not because they are traveling through space at that speed, but because space itself is stretching. This means there are regions of the universe we will never reach, no matter how long we travel. They are permanently beyond our causal horizon. While this effect does not isolate stars within our own galaxy, it illustrates a broader principle the universe contains built-in horizons, boundaries beyond which interaction is fundamentally prevented. When we gather all of these constraints, finite light speed, exponential energy demands, relativistic time dilation, ecological fragility, radiation hazards, cosmic catastrophes, sociological instability, technological evolution, motivational shifts, and cosmic expansion, a pattern emerges. None of these barriers alone may be absolutely insurmountable in principle, but together they form a web so dense that practical interstellar contact becomes extraordinarily unlikely. It is like attempting to cross an ocean where the water is poison, the winds are chaotic, the ship requires fuel greater than any civilization can produce, and the destination may disappear before arrival. Each obstacle compounds the others. This perspective reframes the Fermi Paradox in a quieter way. The question may not be, where is everybody? But rather, how could anybody ever get here? If even one of the barriers is absolute, if faster, then light travel is forever impossible. If sustainable generation ships cannot remain stable for millennia, if energy requirements remain prohibitive, then galactic colonization stalls at the very first step. Every civilization remains in orbit around its native star, sending signals that fade into noise long before they reach another mind capable of hearing them. And what does this mean for us? It means that Earth may not just be our birthplace, it may be our only reachable sanctuary. Mars, the moons of Jupiter and Saturn, and perhaps distant exoplanets reached by robotic probes could extend humanity's presence slightly outward, but the dream of star-hopping empires may remain fiction. The future of humanity, if it endures, may unfold within the boundaries of our solar system. This realization can feel isolating, even lonely, but it can also feel grounding. If the universe has indeed built walls between civilizations, then the connections we form here, across states, cultures, and continents, become infinitely more precious. Imagine once more that distant world orbiting another star. Its inhabitants may be looking outward right now, calculating the same distances, confronting the same equations, recognizing the same limits. They may feel the same mixture of curiosity and melancholy. We may never meet them. We may never exchange even a single photon of intentional communication. Yet in a strange way, we are united by the same constraints, the same physics, the same silent cosmic architecture. And so we arrive at the quiet conclusion of this journey. The reason aliens may never reach Earth is not necessarily because they lack intelligence or ambition. It may be because the universe itself enforces separation. The speed of light stands as a final boundary. Energy scales rise beyond practicality. Time stretches civilizations apart. Space remains vast beyond comprehension. The silence of the sky is not emptiness, it is distance. Not absence, but isolation. As you let these thoughts settle, remember that isolation on a cosmic scale does not diminish the wonder of existence. It magnifies it. In a universe where contact may be impossible, every planet that hosts life becomes unimaginably rare and valuable. Every civilization becomes a unique expression of matter becoming aware. And here, on this small blue world orbiting an ordinary star, we have the extraordinary opportunity to cherish and protect the only home we may ever truly have.